Through the ages, the map has been a fundamental mode of communication. It attempts to transform the world, incomprehensible in its vastness and diversity, into a comprehensible form. Map makers of old, drawing from travelers' tales and their own imagination, created images of the world as they wished it were. Map making today, though, is a sophisticated science. The static paper map is becoming a thing of the past, replaced by fluid, computer-generated images that can be instantly updated to reflect change. Perhaps most significant, space-age technology is giving us a new view of the world's natural resources, with ecological, economic, and political implications that we're just beginning to appreciate. Later in the program, we'll look at some examples of how today's maps are made and used. But first, a bit of cartographic history from the U.S. Library of Congress. The library has a massive collection of maps, over 4 million, and the chief of the map division, John Walters, loves to show it off.
It's hard to tell who made maps first. I think that if one watches primitive peoples of today drawing in the sand with a stick and indicating direction and point of origin and point of departure and point of arrival, perhaps maps were made thousands and thousands of years ago.
This is a replica of a stick chart like the kind Captain Cook discovered in the mid-1700s on his first Pacific voyage.
No one knows how old they are or how ancient the tradition of using this kind of chart is, but it must be quite ancient. In this case, it's of an area in western Micronesia. The shells represent islands, atolls. The curved strips of bamboo represent current lines, and the basic framework is the north and south piece.
This map is based on the vision of the world held by Ptolemy, the 2nd century Greek librarian. Ptolemy compiled a book of latitudes and longitudes, which was lost and rediscovered in the 15th century. At that time, the information was translated into map form.
The Greeks did know the world was round, or postulated it was round. They hadn't been around the world. They had a pretty good idea of the size of the world, surprisingly not much different than the actual 25,000 or so miles of today.
For nearly 1,000 years after Ptolemy's cartographic breakthroughs, most maps were more symbolic than realistic. This is a 19th century reproduction of a 7th century map by Isidore of Seville.
It's an example of what we call a T&O map, being a circular map with a, if you can imagine it, a T or a cross here, separating the 3 known continents of Africa, Asia, and Europe.
Cartography moved ahead again once Ptolemy's work was revived and inspired the great explorers.
This is a replica of the globe of Martin Behaim, which was constructed in 1492, the same year, of course, that Columbus sailed the ocean blue. And the ocean is blue on the globe, but it does not have anything that of Columbus's voyage in it. It was a conjectural piece showing the distance from Spain or the west coast of Europe to Asia as being rather close, with very little in between. With the exception of this very large island, named by Marco Polo, as a matter of fact, Cipangu, which must represent Japan.
This is the first world map believed to incorporate any of Columbus's discoveries. Dated 1500, it is signed by Juan de la Cosa, who accompanied Columbus on several voyages to the New World after 1493. America and Asia are joined together as one continent without an ocean separating them. To meet the growing need for navigational guidance, a Dutchman named Lucas Wagener produced this Mariner's Mirror in 1585.
It is the first time that in combination we have charts, sailing directions, and a navigational manual. This is constructed so that the mariner, when approaching the coast, would have landmarks to guide him in. For instance, this hill is surmounted by a pillar. One goes directly down here. Here is that hill right on the coast. This is a windmill. This is a windmill. Both of these windmills appear here on the coast. The estuaries, or the mouths of the rivers, are expanded. The numbers here indicate the depth in fathoms. In this case, 30 feet, 24 feet, and so on. These indicate shoals to avoid. And since this is the south coast of England and an agricultural area, there is some cartographic license here with field patterns and houses shown, and sheep, of course, grazing in the fields.
This map from 1669 shows that despite steady progress in the 17th century, cartography suffered an occasional setback.
The myth of California as an island lasted almost 100 years, and it was finally put to rest in the early 1700s by one of the great French mapmakers, Claude Delisle.
The first truly scientific map with exact longitudes and latitudes was created by another great cartographer, the astronomer Jean-Dominique Cassini, in 1699.
It all depended on the telescope. Jupiter has several moons, and one could observe the eclipse of these moons as they rotated around Jupiter, as they passed behind Jupiter and came out again. It took a certain amount of time, and at the time, one could then determine the time of rotation, eclipse, and reappearance at different places on the Earth. If one observed this and took the time, one could then determine what the local time was at that period, and the difference between their local time and the time of the Observatory of Paris, which was doing exactly the same measurement, the difference between the two would be the longitude. The latitude was easy to get with the pole star or with the transit of Jupiter, too.
Cassini's revolutionary approach to map making launched what has come to be known as the Great Reformation of cartography. Over the next 2 centuries, more extensive exploration on land and sea, together with increasingly sophisticated tools for surveying, made maps more detailed and precise. The major breakthrough that brought cartography into the modern era was the marriage of airplane and camera, first joined during World War I. Aerial photography used for military reconnaissance became sophisticated enough by 1962 to reveal proof of Soviet military installations in Cuba. But the technology aboard the U-2 plane could be applied to a more peaceful purpose as well. From its vantage point, 12 miles above the Earth, the camera could record hundreds of square miles in a single frame. The aerial photograph, while not a map in itself, provided detail of vast areas never before available to cartographers. Once it became possible to get a perspective of Earth from space, a second revolution in cartography began.
It is a cartographer's dream to be able to view the Earth from such a height, because you can actually see the Earth, the rivers, and all the various land use patterns as they are in a very, very large area at one glance.
Traveling 570 miles above the Earth, a satellite known as Landsat can create a map of the entire world in 18 days. The scanning mirror of the satellite receives radiation from the Earth. The radiation includes visible light reflected from Earth objects the human eye can see, as well as infrared, which the human eye cannot see. The satellite transmits the radiation information as streams of numbers to a ground station, where the information is stored on tapes. Computers process the information into pictures, assigning false colors to radiation in the invisible part of the spectrum. Different objects reflect light in different ways, and the images are processed so that differences are distinguished by color. One place where mapping via satellite has had a significant impact is Bangladesh.
Satellite mapping is very important for a country like Bangladesh because of the extremely dynamic nature of the environment. Bangladesh undergoes extreme changes seasonally with the floods that come in during the monsoon season. And during the dry season, areas that were normally flooded become very dry and parched. So they have this extreme cycle of flooding and dehydration. And the population pressures are also very large. The population of Bangladesh is roughly 1/3 that of the United States, yet these people are living in a river delta area about the size of Wisconsin. So you have tremendous pressures on the environment.
Major problem is really finding food for all the people there. Basically, it is still a peasant society, an agricultural country. Our agriculture is, to an extent, constricted by the natural calamities that we have to face.
In 1970, 3 million people died from disease and starvation in the aftermath of a cyclone. In 1974, there was drought that brought famine and again tremendous loss of life. Such disasters have brought aid from the international community. The United States helped the Bangladesh government launch a program for using satellite technology to prepare for future natural disasters and their repercussions. In May 1985, about a week after new technology had been installed to replace outdated equipment from the 70s, a cyclone hit Bangladesh once again. This time, weather maps enabled the government to set in motion a disaster alert that saved many lives.
But what is more important than that is this, that the new strides that we are making in food production has been partly a result of the satellite information. For example, Bangladesh has been having for last 5 years an annual growth rate in food production of about 3.5%, much ahead of the population growth. And part of it is due to the fact that we have better knowledge, or the farmers have better knowledge of the soil, the variety, the rainfall, the early drought signals, the flooding signals and things like that.
This is a Landsat image of an area on the Ganges River. This is the same image after computer processing, which classifies different kinds of land use by color.
The agriculture and the villages are shown here in yellow, and the rice paddies, which are full of water, are shown here in green. And then, of course, if there's no rice and the paddy's full of water, it's shown as blue. By using the computer, we are able to get precise measurements of how much surface area is in each one of these classes. And this is very important for planning purposes for agricultural production and flood damage assessments.
More than 5 million people make their living fishing in Bangladesh. Yet there is not enough fish to feed the population. Satellite imagery can show the number, size, and quality of inland water ponds. It also reveals water temperature and currents in the Bay of Bengal, information fishermen can use to locate large catches. In addition, Landsat maps can show the amount of water available. This has promoted more effective irrigation schemes as well as better crop planting. Satellite imagery also can show the health, density, and maturity of various kinds of vegetation. This makes it possible to judge what crops will be in short supply so that the government can arrange to import needed foods.
The farmers are very clever people. Once you can get the information to them, they will do their best. I will give you an example of a new sort of diversification away from rice crop, which has happened in Bangladesh, partly as a result of the information that we gathered from the Landsat images of soil map. We didn't produce any wheat before. Now, in about 6 years' time, wheat has now become about 10% of our total food production. It was in 1979 about 40,000 tons. Today it's about 1.4 million tons. So, you see, one could say that possibly we are leapfrogging into the 21st century.
Problems with rice cultivation became evident in maps created by radar rather than satellites.
We noticed in one area that we were able to actually use the radar to very clearly delineate where the flooded fields were and where the huts were. And by matching the radar image that was taken in 1984 and comparing it against a photograph that was taken in 1980, we were able to see that during those 4 years, the population had expanded in that area, and they needed to scoop earth out of the rice paddies to make mounds to put their villages and their huts on. When that happens, the crop yield tends to be reduced because rice cannot grow very well in deeper and deeper water.
The radar used for mapping emanated from the space shuttle. Radio signals sent from the shuttle bounced off the Earth. The returning echoes were processed into images. As a mapping technology, radar has a distinct advantage over Landsat. It can penetrate cloud cover and other things that can block a satellite's view. In Bangladesh, NASA scientist Mark Imhoff led a team studying how shuttle imaging radar can penetrate the dense canopy of vegetation that covers the jungle. The scientists worked in the Sundarbans mangrove forest, a protected reserve near the Bay of Bengal. This is the home of the Royal Bengal tiger and work site for over 350,000 people. Products from this area add almost $10 million to the economy each year. Before the shuttle launch in October 1984, the scientists set up test sites equipped with metal reflectors and electrical transponders, precisely located to catch the shuttle's radar signal and retransmit it to the shuttle. 4 months after the shuttle mission, Imhoff and the team returned with radar maps to conduct what's known as ground truthing.
Ground truthing, or finding out what's actually occurring on the ground, is very important because when you're obtaining images of the Earth from a very high vantage point, it's often difficult to relate what the image is showing you to what is actually on the ground. So being on the ground and making maps and taking notes is very important for later then relating to the imagery.
Back in the United States, Imhoff used computers at NASA's Goddard Space Flight Center to organize and interpret the radar data. One of the results is this map, which shows how tides flow over an island in the Sundarbans. The map was created by combining images recorded by the space shuttle when it passed over Bangladesh on 3 consecutive days.
Here it shows the tides very shallow, they're getting deeper and deepest, and then they back off again. This product can be very useful for mapping mangrove forests around the world because the health of the forest, the health of the trees, is very, very dependent upon how the island floods with fresh water and salt water. That cycle is very critical to the health of the forest. The hope is that this technology will be used to better enable various countries that are now developing and developed countries to more fully utilize their natural resources and to harmonize with the environment so that as little damage as possible is done to the environment. And these tools are here now. They've never been here before. And the hope is that mankind as a whole will use these instruments to harmonize with this planet of ours. And it's the only one we have. We better use it right.
Concern for natural resources threatened by overdevelopment prompted another mapping effort a bit closer to home. In Tewksbury Township, New Jersey, residents, worried about construction projects planned for their rural community, turned to Rutgers University for help in mapping environmentally sensitive areas. The Tewksbury residents hope the maps can serve as a guide for saving precious resources and a way of life.
I was born and raised here. My father was born and raised here. And our farm's been in the family since 1863. My grandfather sold enough wheat to the Northern Army during the Civil War to buy this farm, which he paid $10,000 for.
In many ways, Tewksbury Township looks just like it did when Miller Craig's grandfather bought this farm. Miller Craig likes it that way.
I love the land. I don't think I could live anywhere else. I go to visit my daughters. One did live in a condominium, and that was like a jail to me. My one lived in an apartment, and I just couldn't wait to get back to Hunterdon County.
Things are changing in Tewksbury, and it may be that not too far from where these ducks waddle, soon there will be condominiums and apartments.
Tewksbury's change will be the result of some past things that have already taken place, namely the loss of land in the New York metropolitan area, the need to expand the metropolitan area, and the improved highway system that now makes it easier to get to Tewksbury.
Another factor is a ruling handed down by the New Jersey Supreme Court known as the Mount Laurel decision.
That decision requires every municipality to provide a fair share of the region's low and moderate income housing needs. And as a result of providing that additional housing, there will need to be some growth that will help provide the funding to do it.
William Queel has proposed a master plan for Tewksbury to deal with these new realities. Among the initial changes proposed is an office complex on this spot and approximately 600 dwelling units elsewhere. Basil Hone recently moved to Tewksbury and built a home his son designed to blend in with the rural environment.
You don't have a McDonald's, you don't have an A&P, you don't have a shopping center in the town. But those are things that most of us who live here actually appreciate.
Basil Hone is not happy with the amount of development called for in Tewksbury's master plan. He leads a citizens group called LUMAT, Land Use Management Association of Tewksbury, which is trying to propose an alternative approach.
It's our feeling that the growth should be managed, in terms of an orientation in our township that we want to stay as rural, as having as much conservation, as much preservation as is realistically achievable in terms of the pressures of growth.
In the search for solutions, LUMAT turned for advice to Frank Banish, a planner with a conservation orientation, and to Peter Pizer, a professor at Rutgers University. The citizens group commissioned Banish and Pizer to create a series of computer-generated maps that reflects environmental sensitivities to be considered when planning development. This geographic information system is a method of converting data based on aerial photos and pre-existing maps into a digital form the computer can understand. Then it's possible to combine and manipulate layers of data by the hundreds and update quickly as changes emerge.
We use microcomputers, and that represents a big step forward from even 5 years ago, when to do this type of process would have required a computer the size of a room and would have budgeted the size of NASA's.
Tewksbury has a wide range of the types of environmental sensitivities that we as planners seek to protect. Steep slopes, for instance, frequently are heavily vegetated, and the vegetation typically is what maintains their delicate balance. Many of these hillsides will disappear relatively quickly if the vegetation is removed, and the development process removes a certain amount of that. The orientation of cuts and fills, which are the excavations and the location of fill material to accommodate roads and houses and stores, are all the types of things that, if you're not careful and attentive in the site planning process, can create horrendous problems in terms of drainage.
Another feature of concern is wetlands.
Wetlands are areas that perform a housekeeping function for Mother Nature. Basically, they take surface water that is traveling across the land and will ultimately end up in a stream, and they clean it up. In a community like Tewksbury, one of the problems that we have to deal with is the fact that the wetlands are really very minimal in their scope.
Once the mapping work is completed, it's not clear what impact, if any, it will have on planning and conservation in Tewksbury Township. Peter Pizer, though, believes this new technology will prove an invaluable tool.
In a state like New Jersey, we have 7 million people over 7,000 square miles. That gives us over 1,000 people for each square mile. The decisions that we make about land use are irreversible. No longer can we say we have additional land. We have used up all of the land. Every time we look at a land use, we're looking at a land use change from some developed use to another developed use. We need to be very careful and very precise as we make these. They're irreversible decisions.
Whether it involves the data processing capability of computers or the perspectives of satellites, map making means something quite different today than it did for Ptolemy in 2nd century Greece. In the 1980s, maps can give us direction in more ways than one. They can lead us to plan for the best use of the Earth's natural resources, resources that are quickly vanishing. For Innovation, I'm Jim Hartz.